Okay. And we're ready. So, last time we spoke about something called the derivative of a function. This is assuming we can find the slope of the function. How was that defined? What's the definition of the derivative? What does it mean? When we find this limit, what does it mean if it can be computed? Yes?
If it's differentiable, it's continuous.
If it's differentiable, it is continuous, yes. But what does it mean? What does this number mean? If I calculate this number and I get an answer, what is that answer?
Slope of the line f.
Slope of f, slope of tangent line to f. Rate of change of f. Think of how fast f is moving, how fast f is changing in relation to x. Etc. There are many ways to actually think about it, but you should know some interpretations of that number. So, as long as this derivative, this limit exists, we say the function is differentiable. Yes, this also means it's continuous, although it doesn't work the other way around. Something can be continuous and not be differentiable. But once you know it's differentiable, you automatically know it's continuous wherever it is differentiable. We spoke about when something would not be differentiable. The intuitive definition is, if you zoom in, it doesn't look like a straight line at the point. But of course, there are reasons why this limit might not exist. Specifically at sharp corners, where the function is undefined, and where the function has a vertical tangent line. So we spoke about all that last time. One of the most important things we also did last time, besides the definition of this thing itself, was we spoke about something called the chain rule. What does the chain rule say? What's the equation in the chain rule?
D over dx, f, parentheses g, parentheses x, is equal to f prime over dx, multiplied by g prime.
So that's the chain rule that told us how to differentiate composite functions. It is quite useful. In fact, today we're going to derive a lot of things, and the chain rule is going to be very important to these derivations. So, assuming f and g are both differentiable functions, meaning this limit exists, we can differentiate the composition of these functions via this formula. This is called the chain rule. We proved that last time. That was one of the things I had to fill in on the paper for the quiz, and I also asked you to find a limit with the definition, meaning you had to do this limit to calculate it. Yeah?
So whenever we write chain rule, we always have to write the left side of it?
Yes, whenever you write any rule, you have to write both sides of it. So at the bottom I asked you for the product rule and et cetera, et cetera. If you just wrote that f prime g plus fg prime, we're going to see why that's the case. That is incorrect. You have to write this or this. The left side of the rules are important. Anyway, so let's continue. Like I said, we're going to derive a lot of things today. For some, it might be a bit of a whirlwind getting through all of it, but if at any point you get overwhelmed, of course try to understand. But at the very least, whatever I write in the box, just make sure you know that thing. But we're going to develop a lot of important things today. First, let's start with a fun fact, which we're going to use in the first derivation. So, if a and b are greater than 0, they're not equal to 1, because I don't want to risk dividing by 0, then we have a lot of rules with logarithms, but here's one that I don't really remember if I told you, so I'm just going to tell you again if I didn't. We can find the reciprocal of a logarithm by actually switching the base and the number. We can talk about why that is again. set this equal to c, then by the definition of the logarithm, this means what? What? A raised to the c equals to b. What I can do now is take a logarithm of both sides. I am going to take it with respect to b, base b. Now we have a log rule that says power can come down and multiply. What's log to the base b of b? It's 1. B raised to the 1 power gives you b. And so now I can solve for c as 1 over log to the base b of a, which we assumed that was this guy. So we can take reciprocals of logarithm of that. Let's not put that in a box just to do overkill here. We're going to use that pretty much right away, but I don't think it's something that I'll need you to know in general. But that's true. Okay, so here's what I want us to do. I want us to figure out what is the derivative of an exponential. Okay, so if I have something that looks like a to the x, a is a constant in this case, something that looks like a to the x, how do I find its slope? Right? So 2 to the x, 3 to the x, pi to the x, e to the x, that's an important one, remember? How do we actually differentiate something that looks like that? Well, because we don't have any clue how to do it before, of course we'll go by the definition. So this means the limit as h approaches 0 of f of x plus h minus f of x all over h. You'll notice here that the limit cares about the variable h, which means anything that doesn't have an h in it can be considered constant. You might notice that there's a common factor of a to the x here, and a to the x is not a function of h. So by a limit rule, I can factor this outside the limit, and then I'd be left with a raised to the h minus 1 over h. So now, if I can figure out what this limit is, I'll be able to tell you what the derivative of this thing is. And so, to that end, I'm going to do a change of variable. What I'm going to do is set n equals a to the h minus 1. Now, there are a couple things that we would notice here. Then n plus 1 equals a to the h, and I can take log to the base a of both sides, and that will give me h on that side also. Notice that as h approaches 0, what would I say about n? Well, then n is going to approach a to the 0 minus 1, which is 0. So as h approaches 0, my n will also approach 0. So what I'm going to do is I'm going to rewrite this limit in terms of n. And I chose n to be very suggestive. At some point I'm going to have you guys chime in and tell me what's going on. So ultimately we come over here. This is a to the x. I'm going to change this limit to a limit as n approaches 0. The top is going to be well, a to the h minus 1, that is my n. And h, because I'm changing the variable from h, my h is equal to this. Now I'm going to do something. Again, at first you might wonder why I'm doing it, but again, I'm trying to see a pattern here. Write n as 1 over 1 over n. I'm taking the limit as n approaches 0, so I'm assuming that n is not 0. It doesn't have to be. And so I can divide by it. And so we end up in this situation. And so now I would have here, a log rule says I can take this guy and bring it up in the power. And a rule I told you about if not last class, the class before that, limits past continuous functions. The logarithm is a continuous function. We know that it's one of the 6 elementary continuous functions. So this is going to be a to the x times 1 over log to the base a of, I can move the limit inside of this function. The limit as n approaches 0 of n plus 1 to the 1 over n. What's that guy? Yeah, that's E. That's the definition of E. Funny how that pops up. So what we have here is a to the x times 1 over log to the base a of E. Now, if I apply the fun fact that I mentioned before, how could I rewrite this? Right, you switch the base, log to the base e of a. And what is log to the base e? What do we call that?
Natural log.
That's the natural log. The derivative of an exponential function is the original function times the log of the base. i.e., if I want to differentiate a to the x, the derivative is a to the x ln a. And this is something we have to remember. This is a rule that we know now. Now, there is a very special case to this rule. If we set a to be the number e, this means that the derivative of e to the x is going to be e to the x times ln of e. But what is ln of e? Ln of e is 1. So we end up with the derivative of e to the x is e to the x. Now that is actually a very special property. Barring the constant factor rule, e to the x is the only function whose derivative is itself. And that makes it very special. That makes it very convenient. The derivative of e to the x is e to the x. The derivative of a to the x is a to the x ln a. So I can just punch out a couple quick examples here. So if I were to ask, what is the derivative of 2 to the x? Well, it's going to be 2 to the x ln 2. What is the derivative of 17 to the x? It's going to be 17 to the x ln of 17. What is the derivative of pi to the x? Well, it's going to be pi to the x ln pi. The derivative of an exponential is the exponential times the log of the base. This is an important formula, and this is a very special case of that important formula. Now, applying the chain rule to this. Remember, the chain rule tells us to differentiate something when we plug one function inside of another function. So, let's take these two rules and plug something inside. What would happen if I plug a function inside of the x? What will be the result? So let's say I have a raised to the u. So I'm differentiating with respect to x, and I plugged in a function that I'm calling u into a to the u. The chain rule says what? Well, you're going to differentiate the outer function, which we use that rule. Right? X shows up in this position. However, since it's not just an x, we have to multiply by the derivative. So that is the rule in general. If you had to memorize one rule, I would memorize this one as opposed to that one. Because this one actually covers that one, right? If I plug in u equals x, then u prime is x prime, which is 1. We derived that last time. So this formula includes that formula, right? So this is the chain rule version of the formula. And many times when I'm giving you a derivative rule, I'll give you the very basic rule, but then I'll also give you the chain rule version. And the chain rule version is more general. If If you want to memorize one of the two rules that I gave you in pairs, it's better to memorize the chain rule version. And similarly, if I were to ask for d dx of e to the u, so I'm differentiating with respect to x. However, I don't have an x, I have some other function which I call u. This is going to be u prime e to the u. The derivative of an exponential with base e is going to be the derivative of the power times the original function. So I can throw in some silly examples here as well. What if I wanted to differentiate 2 to the x squared plus 1? Well, that is going to be the derivative of the power times the original function times ln of 2 by this rule. What is the derivative of the power? Well, we saw what the derivative of x squared was last time, so that's going to be 2x. And we also saw what the derivative of a constant is. That's 0. And we know that the derivative of a sum is the sum of the derivatives, so 2x is the answer. So this is in fact 2x squared plus 1 ln 2 would be that answer right there. If I were to say, what is the derivative of e to the square root of x, then I can apply this rule. We'll take the derivative of the power times the original function. We don't need to put the ln part because ln of e is going to be 1. And the derivative of radical x, what did we see last time? It's 1 over 2 radical x. Right, so those are just some silly examples. So now we know how to differentiate an exponential function. And we know how to apply the chain rule towards differentiating exponential functions. And again, in general, I'd say memorize the chain rule version because it includes the original version. If my u is x, u prime is 1, so I get the derivative of e to the x is e to the x. Those are the rules. Any questions on applying the rules? We're going to do it like hundreds of times in this class, so let's move on. Now that we know how to differentiate the exponential, let's talk about differentiating the inverse of the exponential. What if I had to differentiate the logarithm? Let's start with the natural logarithm. What's that going to be? What is the slope of the ln function? Well, here's how we're going to do it. I'm actually going to use these rules to help me out, or this one more specifically. Set y equals ln x. Notice that we want y prime. What I can do is rewrite this without the logarithm. How would I rewrite this without the logarithm? Now what I'm going to do is I want to differentiate both sides of that equation. If these two functions are the same, their slopes are going to be the same. Differentiate both sides. Derivative of e to the y? It's not e to the y. What's the derivative of e to the y? Y prime times e to the y. That's how you differentiate an exponential. It's always how you differentiate an exponential. Take the derivative of the power times the original function. Derivative of x? 1. We derived that last time. So we end up with this by differentiating both sides. Now, e to the y is never going to be 0, so I can divide by it. And you might notice here, e to the y is x. So I obtain 1 over x. The derivative of the logarithm, the natural logarithm, is 1 over x. Or with chain rule, I I can say the derivative of ln of anything is the derivative of the thing over the thing itself. Differentiate the outer function, multiply by the derivative of the inner function. If I'm going to remember one of them, I remember this one. The derivative of the natural log of a function is just the derivative of the function divided by the function itself. Let's knock out some silly examples. The derivative of ln of x squared plus radical x is going to be, we're going to take the thing that's inside the ln, and on top, you're going to put the derivative of the thing that's inside the ln. What's the derivative of x squared? 2x. Derivative of radical x? 1 over 2 radical x. Now that is the answer. I mean, you can simplify it a little bit, but that's the answer. Sure, let's just simplify it a little bit. We can actually multiply and divide by, right then, multiply and divide by 2 radical x. And I will get here 4x radical x plus 1 over 2x squared radical x plus 2x. And I could write this as x to the 3 halves if I want. You can write this as x to the 5 halves if I want. But that's pretty much it. That's going to be the slope of that function. What about if I don't have a natural log? What if I have some other log to some other base? Well, we go back to way back to, geez, this is probably lecture 1, lecture 2. We had something called the change of base formula of a logarithm. I can rewrite ln of a to the x as ln of x, log of a to the x as ln of x over ln of a by the change of base formula. Which means the derivative of log to the base a of x is the same as the derivative of ln of x over ln of a, which is the same as by the constant factor rule, I can factor the constants out, and the derivative of ln x is 1 over x. So this becomes 1 over x ln a. This leaves us with another rule. It tells us how to differentiate a general logarithm. To differentiate log to the base a of x, this is going to be 1 over x ln a. Or, of course, by chain rule. Derivative of log to the base a of anything is u prime over u times ln a. Differentiate the outer function, multiply by the derivative of the inner function. Let's do a silly example. When I wrap up all the formulas, we're going to do a bunch of examples to make sure that we know how to apply them as well. So if you don't catch the silly examples, don't worry, we'll do many more, and we'll do much more homework. What if I wanted to differentiate log to the base 5 of x squared plus 1? Then I would use this rule because I don't just have the x. This thing here is like my u. So I'm going to have u prime, which is 2x, over u, which is x squared plus 1, times ln of the base, ln of 5. slope of that function. That's a lot. We can get a lot of knowing how to differentiate an exponential, as it turns out. Here's another thing that's going to be useful in proving another very important rule. What if I wanted to find the derivative of ln of absolute value of x? Now, of course, if x equals 0, that is undefined, but because I put the absolute value around the x, it now works for negative x's as well. So remember, the domain of the logarithm is the x has to be greater than 0. Now I take away that restriction. The x can be greater than 0 or less than 0, just not 0 itself. So it's like I have two logarithms branched out. This guy is, it's like this. Now, how would I differentiate that? Well, we remember the definition of the absolute value, hopefully. This is going to break into two things. It's the derivative of ln x, if our x is positive. It's undefined if x is 0. It's going to be the derivative of ln of minus x, if our x is negative. Now, we already know what the derivative of this guy is. That's 1 over x. That's what it's going to be if x is greater than 0. And what is the derivative of this guy? Well, I can use the rule, derivative of ln of u is u prime over u. We know that the derivative of a constant times x is just a constant. We derived that last time. So this is going to be the derivative of the inside over the inside. You'll notice that that also simplifies to 1 over x. So it turns out that in all cases x is not 0. If I differentiate the absolute value of x, I again get 1 over x.
You need to put the other, you need to put x greater than 0.
Meant to put it less than. So whether x is greater than 0 or less than 0, the derivative of ln of absolute value of x is 1 over x. That's going to be important later when we're doing integration. This is way towards the end of the semester, but that's going to come back up. What do I want to do now? I think now I've told you enough to derive one of the most important rules. It's usually one of the first rules that students learn in a calculus class, but usually it's not proven because without exponentials you can't really prove it in general. So I decided to do exponentials and logarithms first, so now we can prove this rule without leaving gaps in the proof, which is what your calculus textbook does. It says it proves the rule in pieces over many sections, and until it does exponentials and logarithms, it couldn't do it in general. It's not that hard leading with exponentials and logarithms, we just did it. And so let's now get to the other rule. One of the most important kinds of functions for various reasons is the polynomial. It's a very nice function. It's continuous everywhere and it behaves nicely in a lot of ways that we like mathematically. We should want to know how to differentiate polynomials. Now, we know that the derivative of a sum is just the sum of the derivatives. So if I give you a general polynomial, just differentiate each term. If they have coefficients in front, we know that the derivative of a constant times a function is just the derivative of a constant, is just the constant times the derivative of the function. So if I want to differentiate a polynomial, I can just differentiate each part separately and leave the coefficients alone while I differentiate the x's. So really, to figure out how to differentiate any general polynomial, I just need to figure out how to differentiate x to a power. This is called the power rule. Now we're going to derive the power rule. Once I know how to differentiate this, I automatically will know how to differentiate a constant times this, and I will automatically know how to differentiate a constant times things like this being added together, which allows me to differentiate a general polynomial by this constant factor rule and the sum rule. So let's actually figure that out. Set y equals x to the n. Then I'm actually going to take the absolute value of both sides. And this is because you should just know that the absolute value of anything to a power is the absolute value of the thing raised to that power. That's a rule from pre-calc. Anyway. I took absolute values of both sides. Why? Because I don't want to have to worry about when x is negative. Why? Because I'm going to log both sides. Now, why would I log both sides? Now, this is going to be a general principle, right? So what I say now is going to apply for a very long time, for the rest of your life, okay? And it's something that you're always going to be thinking about. What made differentiating this hard is the nth power, right? Remember when we derived the formula for the derivative of x squared? We had x plus h squared, and we had to expand that and regroup and to find the limit. What if it was x to 1,000? You'd have to x plus h to 1,000th power. You'd have to expand that to cancel stuff. So the thing is, when n gets big, that makes it complicated. Now, so here's the important fact. Whenever a power is complicating things, use a logarithm to get rid of it. That's a general fact. Just like how you know if you want to solve an equation and there's something's being added to both sides, oh, just subtract that thing for both sides. As a general rule, you now know, whenever a power is giving you trouble, use a logarithm to get rid of it. And sometimes you might have to modify things a little bit to get the logarithm to work, because if my x here is negative, taking the log of it might actually mess things up. The log will be defined. What I did was took the absolute value of both sides, and now I can actually take the log of both sides. Taking the log of both sides allows me to bring this power down. So now, it's not a power anymore, it's actually a multiple. And it's a constant multiple, which derivatives deals with those easy. It literally leaves them alone and differentiates the guy beside it. So now what's going to happen is I'm going to differentiate both sides. What's the derivative of ln of absolute value of y? Y prime over y by the chain rule. What's the derivative of, well, n is just going to stay here, right? What's the derivative of ln of absolute value of x? What is the derivative of ln of absolute value of x? X prime over x, which is 1 over x, which is what we have right here. So this just becomes n times 1 over x. What I can now do is I can multiply both sides by y. But what is my y? Well, my y is x to the n. Now, by the laws of exponents, what does that mean? If I have x to the n divided by x, what is the result? You subtract the powers, x to the n minus 1. So this means that y prime is equal to n x to the n minus 1. This is called the power rule, ladies and gentlemen. This is a very important rule. The derivative of x to the n is n x to the n minus 1. This works for all non-zero x's. If your x is 0, then you would just have y equals 0 in the beginning, just use the constant rule. We know derivative of a constant is 0. So it technically kind of works here, except if your n is negative, having a 0 plugged into the x is going to be a problem. But for all other x values, this is how you find the derivative of x to the n. Yep.
So when we're writing the formula, if we wrote like f of x to the n instead of x to the n, is that incorrect?
So if you wrote something like the derivative of f of x to the n,
Yeah.
the correct version of the formula in that case would be n f of x to the n minus 1 times f prime of x. If you forgot the f prime of x, it's wrong, because you need the chain rule. This is sometimes referred to as the generalized power rule, which is just applying the chain rule to this. So if you just put the f and not do that, it's wrong. You need the f prime rule. But that's called the power rule. It's a very important rule. It tells us how to differentiate x raised to a power, and it will work for any power. So if I have x to the 5th, well, this is going to be 5x to the 4th. If I have the derivative of x to the square root of 2, what does that even mean? It doesn't matter, I know how to find the slope. That's the slope of that thing. The derivative of x to the e, well, it's the x to the e minus 1. The derivative of x to any constant is the constant times x to that constant minus 1. This is called the power rule. And of course, if I string a bunch of these together, like I asked you, what is the derivative of the polynomial of 5x to the 7 plus 3x cubed minus 4x squared? Well, you go through and you do it one at a time. Constant factor rule says the constant is going to stay here. Differentiate x to the 7th, I get 7x to the 6th. 7 times 5 is 35, x to the 6th. The derivative of the sum is the sum of the derivatives, so I can just do this one separately. Derivative of x cubed by the power rule is going to be 3x squared. The 3 is going to multiply that 3 to give me 9. So that gives me 9x squared. Then, if I want to differentiate that, by the sum factor rule, I just do it separately. It's going to be minus the derivative of that. The 4 is going to stay, and then I'm going to bring the 2 down by the power rule. So that's going to be x, and that would be the answer here. Right? So with the power rule, I can differentiate any general polynomial. It's called the power rule, so let me get this. We can give this one a title. It's called the power rule. Now, there is a power rule for integrals, but usually whenever anyone says the power rule, they mean this guy. If they mean the integral one, they'll actually say the power rule for integrals. They'll actually attach that. But if anyone tells you, what's the power rule? They're talking about this guy. The derivative of x to the n is nx to the n minus 1 for all non-zero x's. So that's important. And the way we proved it, n doesn't have to be a positive integer. N can be any constant whatsoever. The exponential and the logarithm allows us to do this for any constant without having to expand a bunch of terms. What else do I want to tell you about? Oh, I thought I saw a hand just now. So that's the power rule, very important. Never forget it. You put that in a double star. I usually don't write the chain rule version of the power rule because, I don't know. I think it's hopefully more or less obvious. Oh, maybe one thing I can talk about is that with the power rule, we can derive many, not all, because we also did sine and cosine last time, of the rules we figured out last time. So you might have remembered we found what the derivative of a constant was. We know that the answer was always 0. People usually don't forget this, but another way to think about this would be, think of the constant as a constant times x to the 0, and then apply the power rule. Get 0x to the 0 minus 1, which is 0. We also found that the derivative of a constant times x was the constant. Well, it turns out you could apply the power rule. Leave the constant alone, take the power 1, move it down. X to the 1 minus 1 would be the answer, which is x to the 0, so you just get the constant. If I wanted to differentiate x squared, we derive that using the limit definition. But according to the power rule, that's 2x to the 2 minus 1. Again, we get 2x. We also derive the formula for the square root of x. But if you remember your laws of exponents, that's just x to the 1/2. Using the power rule, that's 1/2 x to the minus 1/2, which is 1 over 2 radical x. We also derived very painfully the derivative of 1 over x? Well, I could actually derive that quite easily with the power rule, right? That is x to the minus 1, bring the negative 1 down, subtract 1 from the power. That's minus x to the minus 2, or minus 1 over x squared. So a lot of the rules that we did last time actually follow straight from the power rule. So you can actually forget most of them and just know the power rule. Although those specific functions, square root of x, radical x, constant times x, they show up all the time anyway. So if you just know them automatically, that's also pretty good. But if hell freezes over and you forget them, the power rule actually can save you. Just rewrite it to x to a constant power, and we now know how to differentiate that. Do I want to derive any other rules for you? Presently, I don't think I need any basic formulas now. Okay, so what we're going to do is we're going to want to generalize derivatives even a bit more. In terms of its properties, algebraic properties. Now, recall also last time, we had what was called the constant factor rule. This was the one that says if I take a derivative of a constant times a function, the answer is the constant times the derivative of the function. And we also had the sum rule. Sometimes it's called the sum difference rule. This is the one that says the derivative of a sum of functions is just the sum of the derivatives. So we know how derivatives deal with constant multipliers and sums. So the natural question would be, how does it deal with multiplication? How does it deal with division? So if I were to multiply two functions, what is that? Well, I can tell you what it isn't. It is not. If you differentiate the product of two things, it is not the same as just differentiating each thing and sticking it together. Derivatives do not distribute across products. Right? So yeah, you're adding two things that take the derivative of each part. You're multiplying two things, you can't take the derivative of each part. That actually doesn't work. So derivatives do not distribute across products. It's easy to see this with an example. Let's say I wanted to differentiate x squared. We know the answer is 2x. But what if I looked at it as x times x and decide to differentiate each part? If I differentiate this and get 1, and differentiate that and get 1, I would get 1 as the answer, which we know is not true. That's actually not correct. Right? So we actually know that derivatives do not distribute across products. It doesn't make sense with even the most basic functions. So how do you differentiate a product is the question. And this leads us to something known as, well, no surprise, the product rule. Because math people are very bad at naming things. This rule tells us how to differentiate products. What do you call it? Product rule. So let's actually do that. So I want to find the derivative of a product. Now, if we don't know what a rule means or does in the first place, what do? You go back to the basics. You go back to the definition of the derivative. Because here I don't know what my f and g are, I don't know if they're polynomials, I don't know if they're logs, I don't know if they're exponentials. So none of the specific shortcut rules will work for me at the moment. F and g can be anything, so to figure out how to deal with an expression like that, go back to the definition. Now, we're going to do the usual math trickery. Try to multiply and divide by something that's convenient, or add and subtract something that's convenient, as we did when completing the square. So that's what I'm actually going to do here. I'm going to add and subtract something that's going to be convenient. And you'll see, hopefully, why it's convenient shortly after I actually do it. What I'm going to do is I'm going to subtract f of x times g of x plus h. And then I'm going to add f of x times g of x plus h. So I add and subtract this expression. I'm not changing the value of this thing I'm computing, because that is in fact 0. And you might wonder, well, how does that help? Well, now look at this. I can actually split this fraction in two parts. I can think of this part plus this part. Just separate the fractions. Now, what's going to happen when I do that? Well, if I look at the first part, g of x plus h is a common term. I can factor that off. Let's factor it off to the right. What would I have left over? Well, f of x minus f of x plus h minus f of x divided by h. Plus, if I look over here, now my f of x is a common term. I can factor that off. I'd be left with g of x plus h minus g of x all over h. Now I know that limits distribute across sums, and I also know that limits distribute across products. Limits distribute across both. Limits are really nice. So that's what I'm going to do right now. I'm going to distribute the limit across that sum and then each product. This is going to give me the limit as h approaches 0, f of x plus h minus f of x over h times the limit as h approaches 0 of g of x plus h plus the limit as h approaches 0 of f of x times the limit as h approaches 0 of g of x plus h minus g of x over h. Now let's go through. What's this first limit here? That's the derivative. That is the definition of what f prime is. What is this guy? Well, just plug in h equals 0. Plus, there's no h here, so that just stays the same. Times, well, that's the definition of the derivative of g. So it turns out now I have f prime times g plus f times g prime. This is called a product rule. The derivative of the product of functions f times g is going to be the derivative of the first times the second plus the second times the first times the derivative of the second. Now I'm being kind of lazy here, but to me it's okay if you write down the rule like this. Technically here you can put f of x or g of x, but I'm okay with you not writing it as long as you know what you mean. That is called the product rule. That is a very important rule. It tells us how to differentiate a product of functions. This one's super important. Does this actually work out on the basic example? if I now look at differentiate the derivative of x squared, if I think of it as x times x, is it consistent with the actual answer? Well, if I think of the first one as f and the second as g, I'm going to take f prime times g. F prime is 1, g is x, plus f times g prime. F is x, g prime is 1. I get 2x, so yeah, it actually does work out. I mean, we proved that it would work out. That will definitely work out. But now this tells us how to differentiate a multiplication of various kinds of functions. So for example, if I wanted to differentiate x cubed times the sine of x, let's put some things together now. How do I actually do this? What do we get here? Yeah.
3x squared times cosine x plus cosine x plus x. No, sine x cubed.
Is that right?
I think the first one is sin x.
This should be a sine of x. Right. So you differentiate one at a time, right? So you differentiate x cubed, leave the sine alone. Then you're going to leave the x cubed alone, differentiate the sine of x. So that's the answer. This is called the product rule. You want to differentiate a multiplication of functions, differentiate one at a time, add them together. Pro tip. The product rule generalizes very naturally. I'm not going to write down the general product rule, even though I could. It's just going to be very cumbersome. But let me just illustrate what I mean by it will generalize naturally. It will move on from two functions in a very predictable way. What if I had three functions, f, g, h, and I want to differentiate the product of three functions together? It turns out a very similar pattern will ensue. What you do is you differentiate one function at a time and add them together. So you're going to differentiate the f, leave the g and the h, differentiate the g, leave the f and the h, differentiate the h, leave the f and the g. You can actually do that. If I wanted to differentiate the product of four functions, again, it's going to be very, very similar. So the derivative of h I, right? So if I have four things being multiplied together, how do I differentiate that? Well, essentially what you're going to do is you're going to copy this thing 4 times. And in each factor, in each term, a different function gets to be the derivative. So the product rule actually generalizes very naturally, very nice. So once you know how to do the product rule for 2 functions, the product rule for n functions is pretty easy. You can have n terms where one function gets to be the derivative at a time. So that's cool. But that leaves us with the product rule. What else do we want to talk about? Well, the product rule's cousin. How does it actually deal with division? How do derivatives deal with a division? Well, the nice thing about division is it's actually quite akin to multiplication. I can write a division as a multiplication. And so what I can do is I can take advantage of the product rule here. So I won't have to prove this one from definition, even though we could. And it wouldn't be that hard, it would just be a lot to write down. So what I would do instead is if I have the derivative of this, I'm going to think of it as the derivative of f of x times g of x to the minus 1. Then I would apply the product rule. And differentiate this, leave that alone. Plus, leave the first one, differentiate the second one. How would I differentiate this? Chain rule, what does that tell me? Derive this with the chain rule, what happens?
-1.
Negative 1?
X, g of x. Once g of x, negative 2, multiplied by the derivative of g of x.
Right. That's what the chain rule says would happen. It differentiates the outside, which is a power function. It's just something raised to a constant. So this was the generalized power rule I wrote over there. The derivative of f of x to the n is n f of x to the n minus 1 times f prime. That happens. So now what you notice I have is I have f prime divided by g minus, from this negative sign, f times g prime divided by the g squared. What I can do at this point is I can multiply and divide by g to create a common denominator. And so I get f prime times g minus f times g prime over g squared. And this is called the quotient rule. Why? Because the quotient is the result of a division, and this is a division. So the derivative of f divided by g is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. There are all sorts of mnemonics for this: low d high minus high d low over low squared. I don't particularly care how you memorize it, just make sure you memorize it. It's called quotient. One thing you would notice here is that the top looks a lot like the product rule, except the middle sign is changed. The fact that the middle sign is a negative does have something important, though. The order of the terms in the numerator is important. Okay? You need to differentiate the top first times the bottom, then subtract and differentiate the other one. That's going to be important. If you write g prime times f minus f prime times g, that's wrong. That's not the derivative. That's actually the negative of the derivative. So the order of terms matters. So probably what I would recommend is that if you memorize the product rule, memorize it in this order, and just know for the quotient rule, change the middle sign and divide by g squared. But that is called the quotient rule. So now we know how to do the bonus on the quiz, right? So it asks you, what is the power rule? What is the product rule? What is the quotient rule? Well, these are them. Then it asks you to differentiate a particular function, which you could have done it using the quotient rule or the product rule with the chain rule at the same time. I have a bunch of examples I want us to do, but I think I wanted to do some things first. Let's look at the other trig functions. Now we actually know enough to actually derive some nice formulas with a minimum amount of discomfort. What if I wanted to differentiate differentiate tangent. What is the derivative of the tangent of x? Well, I don't want to have to go through the limit definition. I don't know about you, but I'd rather not. What I would instead realize is that the derivative of tangent is actually the same as the derivative of sine x divided by cosine x. Now, how do I find the derivative of a division? Well, we had the quotient rule just now. That's quite handy, isn't it? All I'm going to do is talk of that as f and the bottom as g, and I'm going to do the quotient rule. So it's going to be the bottom times the derivative of the top. The derivative of the sine of x is cosine of x, minus the top times the derivative of the bottom. The derivative of cosine of x is the negative of sine of x, over the bottom squared, which is cosine squared of x. Now, of course, in the top, what you'll realize you have is you have cosine squared of x minus, well, this negative and that negative multiply to give you a plus, and you get sine squared of x. And if you recall, cosine squared of x plus sine squared of x is 1. So this is equal to 1 over cosine squared of x, which is the secant function squared. In fact, that's just something I expected to know now. The derivative of tangent of x is secant squared of x. Or want to do the chain rule, tangent of anything is u prime times the secant squared of that thing. That's how we differentiate the tangent function. So that's just something we know. Derivative of tangent is secant squared. Memorize that. What about the other trig functions? Well, I'm not going to derive all of them, but I'm going to derive one more. And the other two, they're derived very similar to how I derived these two that I just did. Let's talk about the derivative of secant. So finding the derivative of cotangent is going to be very familiar to find the derivative of tangent. Finding the derivative of cosecant is going to be very familiar to find the derivative of secant. So I'm not going to derive those for you. You should practice deriving them yourselves. Okay, so secant x, this is just 1 over cosine of x. Now, we could do the quotient rule here, but I won't, and I'll talk about that a little bit later, why I wouldn't. The preferred method here would be to bring the cosine up to raise to the -1 power and use the chain rule. So this is minus cosine of x to the -2 times the derivative of the inside. It's minus sine of x. So I end up with sine of x divided by cosine squared of x. Which is equal to sine x over cosine x times 1 over cosine x, or tangent times secant. Which, for some reason, probably due to a mnemonic, people always remember it the other way, secant tangent. So this is also something we know now. Derivative of secant of x is secant x tangent x. Of course, there's a chain rule version. Derivative of secant of u is u prime times secant u tangent u. So, if I were to ask what is the derivative of cotangent of x, it turns out that is minus cosecant squared. If I were to ask you what is the derivative of cosecant of x, it's going to be minus cosecant x cotangent x. And you can practice deriving those. Cotangent is just 1 over tangent or cosine over sine, and cosecant is 1 over the sine of x. Derive it very similar there. Anything else? Okay, that was all. In terms of rules, those are all I wanted to cover. Let's make sure we know how to apply them. To that end, do these. A, find the derivative of sine x over x. stop here. We've been writing a lot, doing a lot. Brains are probably fried. But be sure to attempt these before class on Wednesday. Actually try them out on your own. And then we'll do them in class. We'll start off Wednesday's class by just going through all of these and finding derivatives. We'll talk about some recommendations when finding derivatives, all that good stuff. But for now, I think we can really stop there. Now you know how to find derivatives of a bunch of things. I don't think we're going to cover any new derivative rules for a while. We're going to talk about differential inverse functions like algebra for maybe 3 classes from now. But for now, that should give you enough that you want. See you on Wednesday.